tests and how we choose them, there's these two funny things called null hypotheses and p-values, and we'll have a look at them. Is that all right? Okay, so just to resume, scientists quite often want to know if this group is different to that group, like we were talking about, football players, basketball players, the group I was treating, the group I didn't treat, etc. But the problem is there's lots of ways of being different. Basketball players could be twice as tall as football players, or they could be 1.5 times as tall, or 1.2 times as tall, or they could even be shorter, minus 1.5 times as tall. All of those things are possible, and I could test them, but I'd only be testing one thing of all the possibilities. There's 1,000 ways of being different, and I can't test all those possibilities because it would take forever. But what I can test is, are they the same? Because there's only one way of being the same. You're either the same or you're not. But if you're not, there's 1,000 ways of being different. So I can't really test that. So now this is a heavy bit, this. So deep breath, all right, we can do this. There's the only one question I can answer. What is the probability that I could get the results we got from the two groups if actually the two groups are the same? Right, I'm going to go into that question now because it's a funny question. What's the probability that I could have got those two different means, like those two football players and the basketball players, two different means, but if actually football players and basketballs are the same height? I'll show you what I mean in a second. Remember, we didn't measure every player, did we? We only measured a sample, and that's all we can ever do of anything. If we'd measure every player, we'd know, but we can't. Now then, I've got a graph there, and I've put both graphs together. Okay. These are the graphs we got. The red one, and I'm afraid it's a bit faded, but I hope you can see the red graph there. That's the football players with their mean of 177. And the grey one's the basketball players with their mean of 185. But you can see there's this massive overlap in how tall they are. And yeah, probably the shortest footballer might be shorter than the basketball player who's the shortest. But really, there's a lot of overlap because there's variation. And yeah, the mean height of basketball players is higher, but there's a lot of overlap. So the question is, are they really different? We only had a sample, remember. Look at that. Now, what I've done there, I've done an imaginary extra graph. Now, this is all the sporty people, okay, who play football and basketball and probably tennis and everything. This is just them. And these two graphs are entirely inside that. They're of the same population, okay? Now, I took a sample of these sporty people, and it turns out that the mean of the football players was lower than the mean of the basketball players' height. That might have just been because I picked them by chance. I'll read what I've said here. I might find that all those results only look different because we only had a tiny sample. And we happened by chance to pick some small football players and some tall basketball players. I could have done that. But if I'd picked a different 10 or a different 100 football players and basketball players, they might have not shown any, they might have had the same height. It's just a sampling error. You know, if I asked, if I went into a classroom and said, do you like maths? And I'd asked 3 kids, and I happened to pick the front row who chose to sit at the front row, and they'll say, yeah, we love maths. That's a sample. I'll say, well, that class, they all love maths. What a great maths teacher they've got who makes them love maths. But if I went to the back row and asked 3 kids, said, do you like maths? No, we can't stand it. We hate it. I said, that class hates maths. That's because they've got a terrible teacher who makes them hate maths. It's not teaching them in a way that they like. So I haven't got, I haven't got a representative sample there. But actually, there's a big thing called the class, and they're just in it. And I just made a sampling error, said, oh, look, they like maths. Oh, look, they don't like maths or whatever. You can see that sampling means that we're not really sure if they're the same or not. It was actually the same class. You see what I mean? Okay. So there was a tiny sample of footballers who seemed to be shorter, a tiny sample of basketball players who seemed to be a bit taller, but really, you know, they're all just part of the same population. And it turns out they're not really different. It was just sampling. And that idea that they're really not different is called the null hypothesis. And in this case, the null hypothesis is there's no difference between the heights of football and basketball players. It's the null hypothesis. They're actually the same group of people. Any difference that I saw, that mean it looked different, it's just because of chance, just because of sample size and choosing effects, and the fact I didn't go around every basketball club and I didn't go around every football club. I just chose at random and it gave me some results. But really, they were just the same if I'd counted them all. But I can test the null hypothesis because there's only one way of being the same. And then the other great thing is we can use those numbers, the mean and the standard deviation, and do statistical tests, and it pops out a number and it'll tell us the probability that the results are just due to chance, just due to sampling, they're not really different. The probability that the results are just due to chance. Right, which takes us off. So that's the null hypothesis. A little bit more about it. We can test a null hypothesis. For example, basketball players are taller than football players. That's a hypothesis. I think I've seen basketball matches and I've seen football matches, and some of those basketball players, they can put the ball in the basket without even jumping up. They're really tall. So that's them. But I can't test that because unless I know exactly how much taller I think they are, there's no maths to do it. But I can test the null hypothesis. There's no difference between the heights of basketball players and football players because that means they're both the same, and there's a maths for that. Or another hypothesis, 6 months of intensive speech therapy improves articulation of phonemes. Well, unless I want to get really specific and say it improves it by this much, I can't test that. But the null hypothesis, there's no difference in phoneme articulation after 6 months, blah, blah. Well, I can test that. And I can test it with statistical tests that use those numbers we've just been talking about, the mean and standard deviation. Okay. Now then, those statistical tests spit out a number in the end, and that number is called a p-value. And that p-value is the probability that the results we got, the differences in the means or whatever, are just due to chance. Because we had a little sample of footballers, we had a little sample of basketball players, we had a little sample of this, whatever. So what's the probability that although they look different, it's actually just due to chance? Then these p-values, they're a probability. Is everyone all right? I better stop there for a bit. Is that how it?
Yeah, good.
Perfect, Tristan. Really good, thank you.
Yeah, so
the face is a face of concentration, just listening. Because
yeah,
I'm normally smile all the time when I'm concentrating.
Yeah.
Yeah, no, I'm listening. I'm focused.
Yeah.
Thank you.
So So I can test a null hypothesis, which is why we have to use that. Because I remember people were saying, well, why do you have to, why null hypothesis? Why not just test the hypothesis? Well, you can't, because there's, but the maths won't do it. But there's only one way of being the same. So you can test the null hypothesis, and that's what we can do. So a p-value is a probability, and it's the probability that the differences that you see are just due to chance. They're just due to sampling. So what does P stand for? Well, it's probability, and probability is measured from 0 to 1. 0 probability means it's impossible. There's zero chance of that. It's not happening. That's absolutely impossible. 1 means absolutely certain. It definitely is the truth. 0.5 means 50-50. So what's the probability of heads? Well, the probability of heads is 0.5. What's the probability of tails? Well, that's 0.5. The probability of getting a head or a tail, well, that's 1. I'm going to get one or the other unless it lands on its edge. I don't think it's going to do that. So what does 0.05? Now, Jenny's talked a lot about 0.05, and that's a small number. It's unlikely. It's not impossible. Now, 0.05 is 5%, or it's 1 in 20. Now, I'm aware when I was at school, people played Dungeons and Dragons, and some of those kids had these fantastic 20-sided dice, which I was very jealous of. I didn't really want to play the game, so I couldn't really get the dice. But if you had a 20-sided dice and you roll it, then 0.05 is the chance or the probability of rolling a 20 or whatever. So it's unlikely, but it's possible. So what does 0.001 look like? Well, that's 1 in 1,000. That's the probability of rolling a 1 if you had 1,000-sided dice. I've never had one of them. Right. So p-values are probability. 0 is impossible. 1 is absolutely certain. And the one we're most of the time interested in is 0.05, which means it's quite unlikely. You'd have to do the test 20 times to expect to get it. Okay. So that's the p-values. So a small p-value tells us that there's only a small probability that the differences were due to chance. I'll let that sink in. If it's a small p-value, less than 0.05, then there's only a small probability that basketball players and football players are really part of the same group. So when I do my statistical test, like the t-test or whatever it is, if the p-value is small, 0.05 or less, then there's a small probability that they're actually the same. And that means they probably are different. That means basketball players probably are taller. It's probably not just because you had a little sample. Now, p-values of 0.05 or less make you feel that you've found something out. It's significant. What have I said here? If p is 0.05, there's only a small probability that the treatment we gave made no difference. So if you're reading these papers and the results were significant at p is less than 0.05, then yeah, it probably worked. The treatment probably worked. It's what experimenters kind of want. I know you're not meant to say what you want because you're meant to be impartial, but people who do experiments, they want a result, don't they? So p is 0.005 means you've got something. Something happened. Something interesting happened. If it's bigger than that, forget it. You've got nothing to report. P is less than 0.05. That means your results are significant statistically. There is a difference between the groups. It doesn't tell you what the difference is, bigger, smaller, whatever. So with most statistical tests, the p-value is what you look for. Right. How's everyone now? That's the second kind of PowerPoint. Is everyone still on board? You all right, Sam?
Yeah, thanks, Tristan. I feel like this is making more sense to me than,
Good.
It's really helpful.
Yeah, good. Right. So what have we said so far? We've said groups are difficult because there's not just one number to describe a group. So you have to take a mean or other things, and you have to measure the spread. And the best thing for that is standard deviation, but there's other things as well. And if you've done that, you can describe the group. If you can describe a group, you can use maths to compare the groups. But to do that, you need a null hypothesis to see if they're the same or different. And in the end, whatever it is, you'll get a p-value, which tells you, are they really different? And if it's small p-value, then they really are different. That's really good. Okay, so the last bit, oh God, there's all those tests. How do I know which one to use? And I think actually since I made this, we've done a bit more of this. So this might be okay. We're still asking that same question. And that question might be, is this group different to that group? And I'll just go through it again. Are basketball players different to football players? Are this group who had this treatment better than no treatment? Is this treatment better than that treatment? Etc. That's still the same. Is this group different to that group? And we use our numbers. That's the mean and the standard deviation of the dependent variable, the thing that gives the results. Oh, no, but there's lots of different statistical tests. And we have to know which one to choose. And it depends on so many things. Are the results normal? Do they give one of those nice curves like we had, like the football players? Are they look like that? Is it the same group of people at different times, or is it different groups of people at the same time? That matters as well. There's lots of things that seem to matter, but there's a decision tree to help us find out which is the right test to use. So that's what that thing, that scary thing there, that decision tree is all about, what test to use. Now, some of those questions are a bit funny, so let's have a look at them one by one as we go down the tree. So, well, let's look at the top line. Right, so the top line says, what type of data is the DV, the dependent variable? For us, the dependent variable is height. So we'll think about that. But that's not the only choice. It says nominal, ordinal, or something called interval ratio. So let's have a look at those one at a time. So the first question at the top of the decision tree is, what type of data is the DV? And that's the results that come out. Okay, so first of all, it's nominal. Well, nominal data has a name. So nominal data is like categories, So if I'm tossing a coin, the nominal data is heads or tails. It's two things. On a dice, well, it's numbers, but they're it doesn't matter because it's a dice. I could write anything on those sides. So that the categories I could get is 1, 2, 3, 4, 5, or 6 on a dice. But if it was a dice, I could write on it A, B, C, D, E, F, and G. And they'd be my categories. If you see, I could write anything I want on the sides of a die. If I'm counting people, it could be left-handed or right-handed. They're categories. I can count people. Have you got asthma? Have you not got asthma? I can count and I can put it in. Biologists use it for counting butterflies. Is it a blue admiral or is it a cabbage white or whatever, So you can count things and say, I've got that. That's nominal data. If you count it, put it in categories and give it a name, it's nominal data. And that might be useful Because if you keep rolling the dice and you get lots of sixes, you might think that's a funny dice, you know, I counted. Or you might say, oh, Red Admirals are doing well this year, or oh, autism's increasing in school children because I counted them and I put them in boxes. It's like a tally chart, isn't it? I could just tally. Are you autistic? Yes. Are you autistic? No. Okay, I count it, put it in categories. It's not measuring them. I didn't measure how autistic they were. I didn't measure the number 6 on the dice. And I didn't measure the Red Admiral. I counted them. It's different. So that's one kind of data, is counting data, and that's nominal. So if you've been counting things and putting them in categories, you follow that bit of the decision tree. And there's a bit of a decision tree that goes down here. And usually if you're counting things, I'm not going to go into it, but you usually get to something called the chi-squared test. Now, we haven't done about that because I don't think we're going to use it, because I don't think we often count people and put them in categories. So I don't think we have to know about it. And until someone says we do, we can forget about it. But at least you know what nominal data is. So let's forget that one. We're not going to use it because we don't usually count people and put them in categories in our job. Good. Next one, ordinal data. And that's the middle one in the first question. So is it ordinal or rank data? Okay. So ordinal data is when it's in order, or it's ranked first, second, third. I can put it from best to worst, first to last, big to small, but it's not a measurement. So gold, silver, bronze, or first, second, third, that's ordinal data. It doesn't give me how many seconds they took to run the race. It's just the order they arrived, and it's slightly different. So it's not a measurement again. It seems like it might be, but it's not, because who came first in a test, who came second, who came bottom in the class, that's not their marks in the test. Okay, so that's ordinal data. And I don't think most of the time we'll use that either. So again, let's forget about it. So the next one is what we are doing. These are measurements. So interval, ratio, or scale data, that's this one, the third one in the question. I think that's most of what we are going to be doing, because we do assessments and they get a score, or we measure something and they get a percentage of answers right, or, you know, so that's what we use. Most of the time, it's that interval or ratio data. Things we measure. Scores on tests, height of football players again, although we're probably not going to be doing that, or IQ if that's something you're into, or ability to name colors like in those SPSS things, or ability to recognize phonemes or whatever it was. They're all measurements, and they are percentages or they're scores or whatever they are, and that's what we do most of the time. So that's the route through this decision tree that we're going to take. Okay. Is that okay, everyone? Wow. I'll carry on anyway. We're getting there now. So we're going to use quite a lot of the interval / scale / ratio data, because that's measurements and that's what we do, probably. So let's imagine our basketball players and our football players again. We measured them. So that's interval ratio data. The next question is, are they normally distributed? That was the next question in the tree, or was it decision tree? Yeah. Well, it looked like they were. I remember that's the graph we had. It looks normally distributed. It's nice and evenly spread about the mean, but just in case, like, I can't remember who was asking, but yeah, there are tests you can do, and there's a test called the Kolmogorov-Smirnov or KS test, and whatever that test is, it spits out a result, and you do that on SPSS, and there's tutorials about that, and it says if the data is normal, and most of the time it is, because it's measuring things, or it might be a bit skewed, but it'll either way, We'll find out what to do if it's not, but let's say now it looks pretty normal to me. If the answer is yes, then we go down our decision tree. Are the variances homogeneous? Well, variance is a bit like standard deviation. I know that. But to be honest, I don't know much more about it. But I think it's the measure of skewness and kurtosis. And if it passes those tests, like what Jenny was talking about, those two tests of skewness, is it all bent, the data, or is it all squished and squashed like kurtosis, then I think it's fine. So I'm not going to worry too much about that question. I think for us, it's always going to be all right. If the data is normal, then we don't have to worry about this question. So let's assume it's a yes. Next question, how many factors are there? How many factors are there? How many independent variables? Okay, so the independent variable was what sport they do. Were they football or basketball? But of course, it could be time. And I think for us, is it now or is it then? Is it treatment or is it not treatment? Is it these guys got the medicine, these guys got the placebo? But that's just one thing, one independent variable. You're not changing any more than that. And I don't think you ever will, because you'd be too confused. You wouldn't know what was going on. So we'll just pass that question. Yes, there's always going to be one. Then it's what's the study design? I'm going a bit fast here, but I think most of the questions we don't have to worry too much about, which is why I'm going a bit fast. So I know that I think it's just one thing, the independent variable. Next, how many groups? And then it says between or within. Oh, what's the study design? Between or within. So we, with our football players and basketball players, that's two groups, basketball players and football players. That's the difference between them. But I could be looking at this group in year one, and then this group when they do their A-levels, and seeing, can I already predict what A-levels they're going to get if they come in and they can't speak properly? Is there a prediction there? It could be within the group, the same group at different times. So that's between groups, like two sets of people, or within the group, the same set of people, but later on after a treatment. Well, we did football and basketball, and that's two different groups. So that means I follow my little thing down. How many groups? 2. And that means I have to do the t-test, the independent samples t-test, which I think we might have been looking at in the SPSS tutorial 3. So that was the, I'll just whiz through that again. So that we had this horrible, scary tree with all those questions in it. And we whizzed through it and we just answered, well, I measured something. So it's interval or ratio scale data. Is it normally distributed? Well, it looked like it was. Another funny question, and I think that's all right. So we'll leave that. How many factors are there? Well, there's just one. What sport do they do? That's the only thing. So that's one. What's the study design? Is it the same people at different times? Or is it two groups of patients? And that's within or between. And then how many groups? Well, I've just got the people that got the treatment, the people that didn't. So that's t-test. And if there were 3 groups, well, then it's the ANOVA test. So I can see that there. If it's more than 2, I have to do something else. Right. How was that? Is that all right? We one last little thing and then we're done. You all right with that? Sarah, you all right? Yeah. Okay, so that's that decision tree. But what if it wasn't normal? What if that first question is okay. Yes, we measured something, interval or ratio, but then the next question, it's not normally distributed. What if the answer is no? What if it was skewed? What if it gave us a number that said, oh, this data's got a problem? Well, then I can do funny things with the data. I can fiddle with the data. I can make it the square root of the data. I can do funny things. And that's called transforming it. And I might be able to transform it in some clever way to turn it into normal data. But I don't like that. That seems a bit messy to me. So I don't think we'll do that. I don't think most of the time we'll do that. I think usually we'll say, oh dear, we can't do the t-test because it's not normally distributed. Let's go follow the little tree, and it says no, and it goes back over to the other kind of data. So then I'm going to follow that bit of the tree. If I do my test and I look at my little bar charts and they're all skewed up, and it says this isn't normal data, you can't, it's non-parametric as the phrase goes, you better use something else. So then I go down a different part of the tree and use a different test. In which case I'll just follow it down again. How many factors are there? Well, it's still one. What's the study design? Well, it's still between, because it's still football players and basketball players. How many groups are there? Well, it's still 2, because there's the 2 groups. And then Mann-Whitney U-test, I'd have to do that. I don't know how to do that test, but SPSS does. So I'd just click on that and it would do it. So those are the main possibilities for us in that case. And then if I wanted to know about 3 groups, I was testing the height of hockey players, football players, basketball players. Well, then I'd ask the same thing. Is it normally distributed? Are they homogeneous? Are the variances homogeneous? Yes. How many? And in the end, I'd just come out with a slightly different test at the end, an over test, which again, I don't know how to do, but SPSS does. And I just put the numbers in, and there's a tutorial about that, I think. So there. Now then, how's everyone?
Yeah, good. Thanks, Tristan. That was really helpful. I was just going to ask, sorry, can you just remind me how we would find out whether data is normally distributed? Can you just remind me? I know we can do something in SPPS, but is there a way of just looking at it and thinking that's normally distributed or not? Oh, I don't know if he's gone. Has he gone? I think he's gone again. Can you hear me, guys? Yeah. Does anyone else know the answer to that question?
Yeah, just to look at the bell curve to see if it looks bell curved. It's got that bell curve shape.
Yeah.
That's
Yeah.
normal distribution. If everything's clustered together in that bell curve shape, then that's normal distribution. If it isn't, sorry, Sam's on another call. If it's got like loads of outliers and stuff, then it might not be as normally distributed. Got like loads of dots everywhere else. That's not within that nice range.
Yeah, no, that makes sense. Okay. I did make a note of that earlier on, actually.
Oh, right, I'm back. Is that all right?
Yeah, thanks, Tristan. I was just asking then, but Sam's kindly answered it for me. I was just asking if there's an obvious way of just looking at data and seeing if it's normally distributed, just by looking at it. But I guess that's where like the graphs would help us because we can see that bell curve.
That bell curve, yeah. That's the only thing, and you can do it by eye, and then there's that KS test, and that gives you a number, and that tells you whether or not it's really is normally distributed, which I think is the only thing. Just gonna stop recording.
For me, that was really helpful, Tristan. Thank you so much.
Good.
just stripping it right back and just going right back to the
Yeah.
basics. And
I think that's right. I think that's what people needed, and I think that maybe